Everybody, and welcome back. Remember last time we derived the telegrapher or telegrapher equations using the lumped element model for a transmission line. So I've just rewritten them here for brevity, and you can see we have the time domain version over here and the frequency domain version over here. So what we'd like to do now is work these equations a little bit to see what their implications are. So just kind of taking a step back and looking, say, at these equations here. You notice we have a pair of what are called coupled partial differential equations. So you have the derivative with respect to z over here relates to a time derivative over here in this other function. And then it having a spatial derivative over here implies another time derivative back on my original function here. So changes over here create changes over here, which in turn create changes back here again, and kind of cycle around back and forth on each other. So this is interesting in the sense that usually whenever you see something like this happening, you're going to get some kind of self-creating, perpetuating propagation effect. All right, so let's do some math and see if we can't clarify what exactly that means. So all I'm going to do is just take the derivative over here with respect to z on basically everything. Right, so I'm going to focus just on the phasor domain version here, but you could hypothetically do it on the time domain version as well, and you would get a similar result. But for brevity, we're just going to focus on this one here, and if for some reason you need to do the time domain equivalent someday, it's a very parallel derivation. So the derivative of the derivative with respect to z is simply going to be the second derivative. So I'm going to have a partial squared of v with respect to z squared is equal to, so remember this is all just a constant coefficient, so that derivative is going to fall onto the current term over here. So I get negative r prime plus j omega L prime times the derivative, the partial derivative of I with respect to z. Now you'll notice this term here is actually this term over here. So I put a little circle here. These are one and the same thing. So all I'm going to do then is substitute this thing in over here. And what you'll get is the following. Negative r prime plus j omega L prime times, now this negative times that negative is going to cancel out and give me a positive. So I'll get a g prime plus j omega L prime v tilde, like so. Now this term here is big and it's ugly, so I'm going to just kind of compactify it a bit by defining a little coefficient over here. I'm going to say gamma squared is equal to r prime plus j omega L prime times g prime plus j omega c prime. So this is called the propagation constant for our equation here. So we're going to just substitute back in, and all I'm going to get is the following. Partial squared v tilde with respect to z squared is equal to gamma squared v. Or more generally, what we tend to do is move this over here, and I'm going to get the second derivative of v with respect to z squared minus gamma squared v equals 0. All right, so that is the homogeneous Helmholtz equation. Helmholtz equation, like so. All right, so the Helmholtz equation is very, very important in mathematics and especially science and engineering. And what you can think of as the Helmholtz equation is essentially a wave equation, but in a sinusoidal steady state. So if I did this exact same derivation here, only on the time domain, what you would get is a second derivative with respect to space being proportional to the second derivative with respect to time. So those j omegas become time derivatives, and you'd get some sort of d squared with respect to t squared kind of effect here. So if you remember from partial differential equations, the wave equation usually looks something like partial squared v with respect to, we'll say z squared, is equal to 1 over c squared times partial squared v with respect to t squared. So you can kind of see how the wave equation here shares a lot of interesting features with the Helmholtz equation. there really is just kind of, this is the time domain equivalent of this thing over here. So in the back of your head, you can kind of keep that filed away. We're not going to do a whole lot of work on this kind of equation in this sort of class, because usually we get to assume sinusoidal steady state for most real world situations. Or if we're not doing sinusoidal steady state, we can do a superposition of sinusoidal steady states at various frequencies to do kind of like a Fourier transform effect, and we can convert from one domain to the other using Fourier transform theory. So yes, we're kind of setting this aside, but that's okay because the one is kind of mathematically equivalent to the other if you ever want to go back and forth between the two. So that's very, very important. And of course, I could have also done a similar derivation by taking the z derivative over here, and you would get a very similar equation where you would get something to the effect of partial I with respect to z squared minus gamma squared times I equals 0. So you also can get a wave equation on the current as well. So the idea is that these telegrapher equations, when you mix them and match them, you get wave equations. And so the implication is the only solutions to these equations is both the current and the voltage are these coupled waves. So that's a very important idea, that the current kind of induces voltages, which then induce currents, and they reinforce each other to propagate down transmission lines. So this is where we got this effect of, I start a signal on a transmission line and it bounces around back and forth in accordance with a wave equation. So when we say wave equation, we mean wave in the sense that the solutions to these equations are literally wave-like things. So in the phasor domain, I'm just going to write down the solution for the voltage here and the current. So what you'll get is something like the following. V of z is equal to V naught plus e to the negative gamma z plus V naught minus e to the plus gamma z. So any function with this general form will serve as a solution to this equation. And one of your homework assignments will actually be to show that this thing here satisfies this thing over here. So you notice you don't really have the solution per se yet, but really what we have is a collection of possible solutions. And the solution will generally depend on how you excite the system and how you impose boundaries. And of course, by analogy, the current will also be satisfied by a similar looking equation. So e to the minus gamma z plus I naught minus e to the plus gamma z here. So mathematically, these terms over here, these are right propagating waves. So these are waves that propagate into the right direction, and then this stuff over here, so both the current, these represent left propagating waves. So excuse me, left. Okay, so you can even have a superposition of a left and right propagating wave together, because a superposition of solutions is also going to be a solution to this thing. So we're still in kind of an abstract mathematical space, but don't worry, we're going to start getting much more down to earth and practical in the next few lectures here. But this is just kind of the mathematical foundation for a lot of this theory, and it's very important to kind of have a good familiarity with it because it just underpins everything that's going to happen later on with our study of transmission lines.